So hello everyone, and thank you very much for joining this webinar that we're hosting here at Model AI. My name's Christopher, and well, first of all, welcome back to those of you who are joining us again after participating in the webinar last week. We really appreciate that you decided to come back and spend some more time with us. And for anyone who's joining us for the first time, well, welcome to this second episode of what hopefully will be a longer series of webinars hosted by us, not necessarily always with Model AI people speaking, but at least for now, we're using these to talk about some of the things that we do in Model AI. And I said this last time, but I'll just say it again, that the reason that we're hosting these webinars in Model AI is that we were hoping to travel to a range of interesting events and conferences this year, and obviously that didn't end up being so. I hope you're all staying safe out there. But our response to that was that we thought, well, maybe we could put together a webinar series and talk about some of the learnings and some of the thoughts that we have about AI and machine learning in Model AI, and maybe make it sort of a forum where interested parties could meet and talk and discuss about these things. So today's webinar is going to be sort of like an overview of some of our thoughts and, should we say, opinions about things that we think are worthwhile thinking about when you are building a game and you think that you might eventually want to support artificial intelligence or machine learning in that game. So as you go about planning your game architecture, or maybe you even want to know how can I adapt the architecture of the game that I already have. Well, the webinar today is sort of like put together as a way for us to talk about sort of like at the high level things that we think that you might want to be thinking about as you're going about that process. Obviously, there are sort of like these kinds of things, you can have a lot of opinions about them. So we're certainly not saying that this is the definite truth. But we wanted to provide some reflection points on what could be what can be useful in what we've seen. I should also say this is not a webinar on game engine architecture. That's not our area of expertise. But we're sort of like approaching it from the angle, well, if we were going to implement AI and ML for this game, what would we like? How would we think about it? So for the webinar today, there is myself. My name is Christopher. I'm a co-founder and the CEO of Model AI. Used to do game development in a game studio called Die Gute Fabrik. Also have a PhD in AI for games, and have many years ago background in psychology and psychometrics. And I'm joined by Daniela from the Model AI team. And Daniela, do you want to say hello and introduce yourself?
Hello, everybody. Yeah, my name is Daniele Gavina, and I'm an artificial intelligence researcher at Model AI. My background is I have a PhD in AI for games, and I'm also a software developer.
Okay, perfect. Thank you so much. So I'll be doing the most of the talking over the slides today, and then both Danielle and I will be available for the Q&A session afterwards. Sort of like the very quick introduction of who is Model AI. We are a company that provide AI and machine learning services to game developers. We do that through 4 different products, 4 different applications of AI and machine learning. We call them Model Experience, Model Play, Model Assure, and Model Create. And what we really want to do with these products is provide game developers with a way of leveraging AI and machine learning beyond just NPCs, because that's often what people think about when they think about AI for games. You think about the actual agents that you might encounter, you know, the bad guys that you might be playing against in the game. But sort of like our mission is making AI and machine learning available to as many game developers as possible, for as many use cases as possible, and also to show that it goes beyond NPCs. But there are many interesting applications of machine learning in modern games, and that's something we want to enable. Whether you end up working with us or people like us, or if you want to build your own stuff, we just want to raise awareness and sort of like get the conversation going about these things. So today's format is we'll spend the next 25 to 30 minutes talking about game architecture, first for collecting data, getting it out of your game. Then we'll talk a little bit about game architecture for enabling training bots and also for bots based on search. Um, then we'll have some sort of like characteristics for game engines and AI project architecture that we think is useful for AI and machine learning. And we'll just briefly talk about who are the typical stakeholders when you're implementing AI and ML for your game. So very sort of like pragmatic, very straightforward. Most of it will be based on sort of experiments we've done on our own and things that we've seen in projects where we've been influencing AI. And at the same time, we'll be running the a QA. So there's a QA box here in Zoom that you can use to ask questions along the way. Daniela and Benedicta from our team will be monitoring the QA section as we go forward. And some of the questions they might be able to answer as we go through the talk. And otherwise, we'll have like the last 15 minutes to cover any questions live that might come up. And hopefully we can get through all of them. We'll answer as many as we can. And we'll also be recording this webinar. So if you need to go or if you miss out on something, we'll be posting instructions on Twitter or through our newsletter in terms of how you can access this and the prior and the following webinars that we're doing. So that's about it. Without further ado, let's jump into it. And now the question that we kind of like wanted to answer today, or the fundamental question that begot the webinar that we're having now, was we were sitting around and thinking, well, maybe a really relevant question when you're planning a game project is, when does my game architecture matter to my ability to later use AI and machine learning for building my game? Because we come across a lot of games, and when we're looking at a new game project, like one of the things we're always thinking about is, well, is this a good match for implementing AI and machine learning? And we also touched about that in the webinar that we had last week. So sort of like which games lend themselves naturally to AI and machine learning. And that depends partially on the game genre, but it also depends to an extent on how you put your game together as you're architecting it. So that's what we wanted to sort of like dive into today. We want to focus on two use cases, which we think are the sort of like the two places where you can get a lot of impact in terms of your game development process by thinking about this before you start. And the first one is sort of like, how do I set up my game development project so it's well suited for modeling my player and my audience experience? How do I set it up so I get the most amount of information and in the easiest way can sort of like extract information about what my players are doing, what they're experiencing, who they are, how to make the experience better for them. And the other aspect we want to cover is game playing bots. So how do I set up my game project from the get-go so I support sort of like the widest range of game playing bot methods, so that you sort of like have the freedom to make the choice later how you want to implement that. When we're talking about sort of like the player and audience experience part, what we'll be talking about here is how to best set up telemetry collection from player sessions. What should we think about when we're sampling from large player bases? What should we think about when storing data? And how to make sure that we enable ourselves to capture and classify player actions or predictions so that we can even run some, to some extent, run live prediction when we need it later. And for game playing bots, we'll be focusing a lot on, well, how do I make sure that we can support things like tree search efficiently in our game? How do we support reinforcement learning and related techniques? So a lot of the sort of like cutting edge, deep learning based machine learning techniques. And what should we be thinking about? And this is a stumbling block that we often run across. What should I be thinking about when I'm putting the observation space together, when I'm sort of like putting together the way that the game presents the game environment to bots? So those are some of the things that we'll be covering there. And before we sort of like dive into sort of like the more pragmatics and sort of like the details, I just wanted to paint a picture for you in from sort of like the AI ML development perspective. If you asked any AI or ML programmer or developer that would be implementing some of these techniques for your games, what would be their dream scenario in terms of the game project and the game engine? I think most of them would answer you with a diagram that looks more or less like this. If you are thinking just about what would be the ideal development environment for AI and ML, well, you would want a game system that is completely deterministic, which means that whenever you put the same input into the game, you get the same output. Um, a system that sort of like supports the copying of states and the loading of states. So you can go to any place in a timeline, you can roll the game forwards, you can roll the game backwards. You can sort of like visit any place on a timeline in a chain of events without any problem and roll it back and forth. And as part of that, you can generate complete replays. So you can record anything that a player was doing or anything that a bot was doing, and you can then use that to replay that deterministically later. So you get sort of like a 100% high fidelity representation of what happened in your game. That's sort of like the ideal environment for doing a lot of this work on AI and machine learning for games. And obviously, it's not always feasible to do that, to build your game that way. There could be limitations to the engine that you're using. Maybe certain events of the game are driven in a way that you're just not able to implement that. But sort of if we look at it from an idealistic perspective, this is what we'd like to be working in if we were thinking only about the AI and VMO. And if you do that, well, you can end up with an environment that's really great for both for collecting information about players, but also for training and running bots. Here's an earlier project that we did in a group under Daniela's supervision at an earlier point in time, where we're having an engine that supports that really allows you to train agents that learn how to navigate and act in an environment all by themselves. Well, not all by themselves, but driven by reinforcement learning. But the first thing we should talk about is the player modeling aspect. So if you want to support player experience capture, if you want to support audience experience capture, if you want to get the telemetry data that is necessary for supporting that kind of modeling, what should you be thinking about? Well, for those of you who joined the webinar last week, one of the things we talked about there is that when you're looking at any game's design, there's typically sort of like an intrinsic level at which the important decision making of the game takes place. So when I'm putting my game together as the game designer, as the whole implementing team, we would typically immediately be able to tell you where do the important parts of the action happen in the game. And that's exactly the same point where we think you should be annotating your events and sort of gathering telemetry from your game. And that's what we call sort of like semantic annotation of the game space. That's making sure that you capture information about what goes on in the game at the meaningful places, so that you have events that fire and get sent through your telemetry system when sort of like the really important player decisions happen. And depending on the game genre, this could be widely different. But if we take the example of a first-person shooter, for instance, well, typical sort of like important events in a first-person shooter could like switching your weapon, firing, using a power-up, switching from sort of like offensive mode to defensive mode, or maybe using the scope on a sniper rifle. But crucially, more than just tagging and grouping events in terms of like what they mean, we also often find it important that you annotate the space that the player moves through. And again, this is really easy to sort of like imagine for a first-person shooter game. For instance, you could subdivide your level into things like a melee zone, a sniper zone. You have stairwells. It would make sense because there's sort of like a conduit and connect different parts of the level. Or maybe if you have an outer perimeter where different kinds of gameplay take place, you could also annotate them and just sort of like measure whenever a player spends time there, because that gives you important information about what kind of the game, what part of the game they like to interact with, and sort of like their play style. Concrete example of what that could look like. This is an internal demo that we developed here, where we implemented our model experience telemetry solution. But what you're really seeing here is a first-person shooter game, and you have the events running at the bottom of the screen. And every time that the player moves to a new part of the level, every time that they shoot, every time they switch their weapon or they hit an enemy, well, we simply just drag it, and you can see that down in the console here. I'll just play the video again so that you can see it. Sorry about that. There you go. So if you keep the eye on the console, you'll see the different events firing there. And every time the player goes through, so now we're passing through the doorway. Oh, we changed the weapon. You're seeing that we're equipping, unequipping the item. You can see sort of like the different environment interactions being tracked. And this kind of like low-level telemetry is useful both for making sense of the player experience, but the added bonus of this is that this is also sort of the kind of interaction data and the tracking data, especially if you're collecting positional data at the same time, that you can use to train bots using imitation learning down the line. Let me just clear this. One question you might have, well, isn't that sort of like a huge onus on the implementing team, both from the programming side and from the level design side, to set this up? But in our experience, it's actually something that you can even add it at the end of, for instance, a level design process, and simply add sort of like these subdividing colliders to your level, and use that to just sort of like at the gross level subdivide your level into the different meaningful aspects. So what you're seeing here is the process that we went through in order to identify the different regions of the map that mean different things. And a process like this for a small level like this shouldn't take too long. Of course, depending on your game size, it can vary it can vary quite a lot. And if you're doing a game that isn't necessarily 3D spatial, you might want to think about different ways of annotating, sort of like where is the player character, what is going on, what part of the game is the player interaction with, what part of the environment is the player interacting with, but the principle sort of remains the same. And if you capture this kind of like detailed telemetry information, that really makes you capable of sort of drawing deep models and building deep models of player behavior. We have an example of this right here. This is just an internal demo that we built at Model AI. But it turns out that I don't know how many of you play PUBG, PlayerUnknown Battlegrounds, but we put together a demo internally because we realized that PUBG actually exposed their API, their event API for all the matches that are happening on PUBG. And not only that, it's a really good example of sort of what we consider best practices in terms of telemetry and event annotation. So if you go and check out the documentation for the PUBG interface, you can basically use that to track everything a player is doing in a PUBG match. And just to show what you can leverage this kind of information for, what we did for this demo is that we mapped it to the engagement of the audience who are watching famous streamers. And then we grabbed the Twitch videos corresponding to this like detailed telemetry. And then we used it to not only make sense of everything that's going on in the game at any given moment, we can even use it to sort of predict the engagement of the audience over different parts of the session. And we can see what all the players are up to and what they're doing in different parts of the game at different times. So this is really just to highlight that if you go through the work of implementing this sort of like deep kind of telemetry, this deep level of tracking, well, then you can really reap some benefits in terms of the modeling that's possible on the other side of it. Of course, this sort of like opens a question about sampling, because if you're doing this like level of low-level telemetry collection from your players, one thing you might want to consider is, do I really want to collect data from all of my players, or do I maybe want to limit myself to maybe just collect data from 1 or 10% of my player base? It really depends on how large, how many daily active users you have, how big the data sets are. But of course, these things can grow in volume over time. So setting up your game for sort of like deciding either at random or based on an instruction from the server whether a player session gets collected or not can be a useful thing to think about in terms of your game architecture. This is also something that we support in Model Experience. You might also want to think about stratified sampling. If it turns out that some kinds of players are more typical in your game than others, well, maybe you want to oversample some of the groups because you want more of that behavior for bot training or for data analysis later. So those were just like a few quick thoughts about how should I instrument my game, what kind of like telemetry is useful for doing player modeling and later driving bot behavior. What should I be thinking about as I'm setting that up? So that's probably a good time to step over to have a conversation about the other part of this, which is what should I be thinking about when I'm setting up my game for supporting game playing bots? What should I be thinking about if I want to use things like search or machine learning, the methods that we talked about last week for building agents and bots that I might want to be using for quality assurance or for balancing my game, or even for showing the players as player-facing opponents in my game. And well, there are a lot of things that you could think about, but four important ones that we consider are, of course, speed. I think everyone who does game development cares about that, or at least it's a useful thing to have. Stability in terms of observations and in terms of like trusting the information you get from the game engine across sessions. Determinism, if you can achieve it, is something that is highly valuable in both search and machine learning bots, and good observations. So those are sort of like the four things that we definitely think it's important to pragmatically think about when you're planning out your game project's architecture. And I'll step through them sort of like one at a time. So talking about speed, well, speed is obviously always a quality that people are probably looking for when they're putting their game project together. You definitely don't want it to be slower than necessary. But in particular, when we're looking at the search-based methods that Nils also talked about last week, speed is paramount. If you want to use modern tree search methods, such as, for instance, here you're seeing Monte Carlo tree search, it's important that you can roll out and simulate as many states in your game as possible. So this becomes sort of like really, really key. In the same way, when we're talking about reinforcement learning, the faster your game runs, the more observations the agent can get from your environment, well, the cheaper this is going to be in terms of computational cost as you're training your agents, and the faster you'd be able to train them actually. So this is like always key to like getting performance for your bots, whether they're based on search, machine learning, or a combination of the two, if you're going sort of like the AlphaZero route. But there are certain caveats and things to be careful about when you're sort of like building your game for speed. Also, in certain cases, you might also be tempted to run your game at a faster speed than the frame rate that the player experiences when they're playing the game. And typically that goes well. But in some cases, when you speed up the engine, you could inadvertently end up having different code behavior depending on what engine you're using and how your project is put together. So you're looking at Unreal Tournament free here. And the reason that you're doing that is that we just wanted to show some results that we did from a study where we tried to investigate what does it actually mean, sort of like pragmatically, for an existing game to speed it up when you're integrating bots and agents into it. So in this case, we have two bots playing against each other. So we have Team Red and Team Blue, and they're playing against each other in the Unreal Tournament free engine. And what you're seeing here is the win rate of one bot versus the other bot. So it's sort of like how often do the outcomes, like how often does the red bot win and how often does the blue bot win. Now, if you notice this graph here, we're looking at sort of like the base case and the place where the AI developer implemented the bot and probably experienced it at sort of like 1x. So this is the game speed, whatever game speed it runs on at the developer's computer. We have one distribution between these two things. But as we start speeding up the game, you'll start to see that this can vary wildly as we run to different game speeds. And it's probably because the game wasn't architected necessarily ahead of time in order to support this kind of like speed up. So whenever, depending on which game engine you're using, it's definitely worthwhile thinking about, well, what's the impact on the whole code base when I speed it up? And you probably want to be running these kinds of tests in order to make sure that your game engine supports it if it didn't already, if it doesn't support it out of the box. That sort of like brings us into the question of stability and determinism, because if you have a deterministic game engine, you avoid a lot of the issues that you're seeing here, because at that point in time, it doesn't matter how quickly you're running your game, because it's deterministic. You should be able to run it at any frame rate and get the same results, no matter sort of like how quickly you step through it. And just to show you sort of like an example of a non-deterministic situation, this is a small experiment and sort of like demo of this that we implemented in Unity. What you're seeing here is the fact that the physics engine typically is the main source of non-determinism in game engines. And what we have is like a little box here where we recorded a player controlling it, and we measured every step of the way through the environment where the box went. And then on the graph over here on the left, we're measuring how much the position of the box deviates from what we were expecting. In other words, we're measuring the non-determinism, how much noise gets injected into the replay versus, if it were a perfect replay, it would be completely flat, the line that you're seeing here. On the right-hand side, you can also see an example of we put a barrier in the way just to show sort of what happens if we completely desync from the replay. But the point here is that as soon as the box that you're seeing touches the sides and starts interacting with any of the physics colliders, well, we get a major spike of desynchronization. And of course, we never recover from that. Like once we're sort of like desynced from the replay, we can try and get back to it, but we're never going to get back to like a 100% fidelity in terms of what happened in the actual player recording. So how can you sort of like overcome this? There's not a sort of like a clear answer to it other than implement like using game engines that are deterministic. I know there are some game engines on the way or already encouraging to do it, or you could sort of like roll your own part of the engine in order to do that. If you're familiar with, for instance, the quantum engine, well, that's an example of one of the newer frameworks that actually provide deterministic physics and game logic and sort of like avoid this problem. Here we're seeing another example of it in a racing game, where the little car up here is trying to trace the green line, which is what the player actually did. But as sort of like time progresses, it desynchronizes and it sort of like drifts away from the replay that the player had. It doesn't mean that you can't use bots in game engines that aren't deterministic, of course. It just means that in those cases, your machine learning algorithms or your search will have to compensate for it. So what you're seeing here, for instance, is an example of that, where, well, if we apply sort of like a mix of imitation learning and reinforcement learning, well, we can get an agent that still learns to replicate the player's behavior as well as possible, even if it doesn't match it like 100%. So you can still learn around these things and search around them. It'll just make the task a little harder. The final thing we should probably talk about is environment observations. So when I'm building my bot, how should I put it together in a way that ensures that it's efficient and that my agent observes the part of the game, my bot observes the parts of the game that are relevant to it. And we have a couple of like concrete examples for how you could go about it for different purposes. The first one we have here is a bot that we trained to replicate human behavior. So an example that we got from a human. What you're seeing here is like the green little ghost is what the human originally did, and the colored corgi is the AI agent that's trying to replicate that in the face of a level that has changed since we did the recording. And as you can see, it does that sort of like relatively successfully. It's following what the human did. So how does this bot that you're seeing right here perceive the environment around it? How is it seeing the game? Well, for this particular training process, we implemented it simply using raycasting. So what it's doing is that we just put a bunch of sensors on it that are observing the environment. It also knows where some of the important objects in the level are, such as the coins and the goal. So again, using the semantic annotation that we talked about earlier. And that is actually sufficient for it to train to the level that you saw before. And I think, yeah, there you go. It made it all the way to the end. So for something like a platforming game, doing these kinds of raycasts in order to observe the environment is sufficient. It also scales to 3D examples. Here we have it for the car racing example that you saw before. And in the same way, we've instrumented the car with raycasts. So that's how it's observing the race course around it, the other cars that are in the level. Now, as you move to other kinds of games, you can sort of like start seeing the limitations of this approach. So a third approach that we found successful in terms of making the game environment available to the bots to train from is making sure that we can export the geometry of the map as sort of a simplified representation So what you're seeing here is actually sort of a grid that we calculated over the actual geometry of a level that we're currently working on with the customer. And then this is sort of the information that we feed to the agent from the agent's perspective. Um, but the key message across all of this is that generally we find it useful to find a way to efficiently communicate the game state with as little data as possible. And sort of like finding the fit that is correct for different game genres is sort of like the trick there. One question you might have, based on the conversation that we had last week when we talked about game playing bots, is what about pixel data? Can't we just make agents that play from pixels? And you might recall that Nils showed you this example here, which is some work he did, where you have a bot playing Doom, working solely from the pixel data that it's seeing on the screen. And it's definitely something that's possible. Obviously, there are other examples of that out there. Alpha Star comes to mind as a great piece of work that does exactly this. But the tricky thing, of course, is, or like where we see the limitation with these kinds of approaches, is that if you want gameplay behavior that is really good, and you want to do it in a way that is computationally feasible and on a budget that sort of like works with most game productions, it tends to grow out of scope pretty quickly. But you can get interesting behavior if you hook directly into the agent, but into the game engine. But for the pixel-based stuff, that's only like at least so far sort of like a viable method for games of a certain scale and budget, or for games that have a relatively simple decision-making space. But I have no doubt that that will change in the future. And a lot of work is happening in that direction, and we're also working a little bit on that ourselves at Model. So we wanted to try and pull together sort of like what are the features, what are like 6 things that we can recommend if you want to make sure that you're building an AI machine learning friendly game. Think about semantic annotation. We think that's really important. That you make sure that all the events that you're capturing from the game are sort of like meaningfully chosen, that they fit the design of the game, what's actually happening in the game. If you can, have fast and ideally deterministic physics. Make sure, if you can, that game logic and physics are separated from rendering and GUI so that you can run your game really quickly on, for instance, a server for training your bots. You can run it headlessly. Obviously, many multiplayer games kind of like get this for free if they have like a coordinating authoritative server in the middle that's also copying the game logic. But depending on your game, even if you're not building a game that follows that architecture, maybe you'd be able to at least enable some of this in order to speed up your training and search in your game. If you can make your game support forward modeling so that you can roll out future states even during runtime or just for bot training, that is sort of like an ideal situation for building game playing agents that use search or machine learning to train. And no matter what you do, what every bot out there and sort of like every AI and machine learning approach will appreciate is a clean way of interfacing with the state of the game at every step. If you're a bot, understanding what is my window for making a decision, and a clear way of sending the actions back to the game using like a very clear-cut interface. Talking about typical stakeholders when you're planning your game architecture and you want to support AI and machine learning, well, what we find is that, and I guess that's the case for so many aspects of game development, is that it actually touches just about all the roles on the team. So if you're talking to the people in charge of production and planning, obviously some of the recommendations, some of the ideas that I put forward here will require some extra planning and some upfront investment. But one of the things that you can use as an argument the other way is perhaps that it'll enable a better understanding of the audience, the players. It might enable automatic QA processes, and it might give sort of like a better end player experience if you can implement more interesting agents and bots in your game. Same thing goes for game and level design. The people who are working on that, I'm sure that the semantic annotation is like an added task. But on the other hand, you get sort of like access to a different level of understanding of your player base if you choose to put that into your game development process. A large question here is infrastructure and operations, very important stakeholders in the sense that they'll have a huge task of receiving all your game data, Or if you choose to work with someone else for this, well, making sure that you get a vendor that knows how to receive this and treat it. And of course, like the core stakeholder in any kind of planning process like this are the people responsible for architecture and programming. And I would imagine for any game project that wanted to support AI and machine learning from the start or down the line, well, that they would be sort of like the key stakeholders in that process. So that was just a very brief overview of some of the things that we think it's important to think about when you're putting your game project together, or if you want to adapt it to support AI and machine learning. You definitely don't need to hit all the targets or do all the things that we recommended here, but if you wanted to set up an ideal case for that, that's what we would encourage you to think about. So thank you so much for your time. We'll step over to the Q&A session in just a second. And before we do that, I just wanted to do a little bit of advertising. We have one more webinar on the books. It's happening also Tuesday next week, so Tuesday again. And we'll get even more specific in that one, and we'll talk about concrete machine learning methods for detecting cheaters and defeating bots with machine learning. So in that talk, we'll go a little bit deeper and closer to the machine learning models. I'll be joined by Chris Carvelli from our team. That's about it. And I think we should step over to QA. And I don't know, Daniela, did you find any questions already that we should think about answering?
So there is a question that's asked how do you handle changes in game design mechanics which should result in new observation space? Can anything be reused from a previously trained agent? It's hard to say. It depends on the complexity of the game space, because for simpler games, I guess that you can actually reuse a train agent with the previous game design with the previous observation space. But obviously, with more complex games such as like 3-dimensional games or like first-person shooter and whatnot, it might be harder to use a previously trained agent with the previous observation space. So it might be the case that you need to retrain that agent from scratch.
Yep, and just to provide an example, we've worked on for instance games that switched from being discrete space, so basically being sort of like board game style, to continuous space over the course of the project, and that was too large a change to sort of like handle. With like we had to rethink some of the the observation space and the models there. It wasn't a huge thing, but of course we had to reconstruct some of the approach. And that's often why we say, the point in time where you want to start working on actually integrating, especially if you're doing bots for the game, is probably around early alpha. I mean, it varies from game project to game project, but usually, once you know that the mechanics and most things have settled down a little bit, so that you're looking more at sort of like additional mechanics that resemble the ones you already have, or you're looking at stats changes, because that really ensures that you can sort of like reuse most of your pipeline and data and so forth.
So there is a second question that is asking if we can provide a more detailed explanation of semantic annotation, because it was not clear to me at first place. So semantic annotation means that you want to annotate to give some semantic meaning to the components of your game, such as the player or like the entities that you can find in your game world. And that can be done either manually, which can be cumbersome because you need to actually annotate everything by hand, or it can be done automatically. For example, if you implement a model view controller or an entity component system game engine, or you're using one of them, it might be easier because it might be that you have a backend that is the game logic that is running and needs to communicate to the front end, which is the rendering of that game. And it might be just a matter of filtering those events sent by the game logic to the rendering, and see which kind of events you are interested in terms of telemetry. So it depends a lot on how you do this. You plan the architecture of your game.
if I can add to that, you could sort of like imagine the difference between maybe you decide to implement an event that's like a zone transition. So you move from one part of the game to the other, right? But what really matters is sort of like the way to make that semantic would be to make sure that you capture the names of the two zones. So it's not just zone transition, but you know that you're transitioning from melee to sniper area, because that actually lets us infer that the people who do that transition often, and then maybe they stay in the sniper area, they have a certain play style. And if you get those tags in there and you get that annotation in place when you're building the game, when you're doing your data analysis, it's going to be sort of like self-evident that that's happening, and you can use that in sort of like the interpretation of the results on the other side.
We have another question that is asking if, based on our experience, what is the speed up of quantum-based deterministic reinforcement learning compared to traditional engines like Unity or Real? So based on our experience, we know that there is an advantage, a big advantage on using quantum, because you can actually do offline replays of your games or your matches, for instance. So let's say that you get for like a simulation for free, because it's just a matter of doing that replay with quantum. So maybe you don't get an actual speed up, because that depends on the game you're implementing. Some simple game you might get bigger speed ups because there is less game logic to compute in every frame. So it depends on the complexity of the game. But the advantage of using a deterministic engine is that you can actually reproduce from scratch the game match, for example, that you are like trying to simulate, in order to collect either the telemetry data that you need, or at the same time the telemetry data that you need in order to train your reinforcement learning agent.
Yep, and if I can add to that, I should say we haven't done sort of like a one-to-one comparison, because we haven't had the same game 2 times in the same engine, but it would actually be interesting to do some more structured experiments. And personally, I'm also really interested in seeing how that would run using something like Unity dots, for instance. So it would be fun to implement the same experiment that makes the same game across like all these different frameworks, but we don't have any hard data.
So then we have another question that says, logging and event capturing systems such as the one you saw in the Unity are also used in other domains of game development, such as audio middleware solution like audio kinetic wise. Have you tried using this data? Would be worth investigating. So at least to my knowledge, I don't really know what this middleware is, honestly. So I'm not sure I can reply on that. So maybe Christopher, you can add something on that.
Yeah, sure. So you know, the audio engine is another source of events, right? And another sort of like perspective of what's going on in the game. And I think what you're asking about, Daniel, and correct me if I'm wrong, is what if we used sort of like the stream and time series of audio events to make sense of what goes on in the game, rather than just like the events that the game developer might have set up and the spatial information. And the honest answer is that we haven't tried it. It's a really fascinating idea, and we have talked about using the audio stream as a way of making sense of the player experience. We haven't done work in it yet, but I think there's there's a whole sort of like avenue of investigation there. Yep. And maybe I can answer the next one, or at least I can start answering. So here's a question that says, it seems like the most requirements to support an AI ML infrastructure to train agents are already present in authoritative dedicated servers in multiplayer games. It opens the possibility to learn from human players' action and create NPCs that play the role of opponents in games. Still, it also creates the opportunity to generate teammate, partners, companions. Do you find that game companies are moving towards this path? I mean, obviously, we can only speak for ourselves and sort of like the games that are already out there in the market, right? But yes, I think we're seeing a larger interest in that, and it's certainly one of the things that our work is premised on, that people would be interested in exploring this. And from an architectural point of view, I completely agree. Like if you have that authoritative, dedicated multiplayer server that you're talking about, you basically have the simulator, right? We're like pretty close to that ideal situation that we talked about in some of the early slides. And I think there are already so, if you think about what's happening, for instance, both in terms of like benchmark competitions, I think that has started some interest in this. But if you also look at the things that have been sort of like hinted at in terms of Google Stadia, and in terms of also some of the companies that we're talking to and working with, I think there seems to be a movement in this direction. And obviously, I believe that we can do really interesting game AI by implementing sort of these methods. I don't know if you want to add to that, Danielle.
Just that from my perspective, I would say that the requirements that you have for multiplayer games are really similar to the requirements that you have to implement AI in your games. That's quite beneficial for both implementing robust multiplayer games and to collect also the data that you need to train, for example, your reinforcement learning agent, or to log the events that you need for the player modeling.
Yeah, but as game design becomes more data driven, and as games become more personalized and keep living for longer times, basically, I think we'll see more and more use of this. Sure. Well, if there are no more open questions, I think we're actually just hitting up on time, on the time that was reserved for this webinar. So I just want to say thank you everyone for coming and taking part in this. If you have any questions that weren't answered here, you can shoot us an email at webinars@model.ai, or you can send us a message on Twitter. And if you're interested in learning more about how to defeat bots with machine learning, well, hope to see you back here at the same time and the same place, the internet, on next Tuesday. So until then, stay safe and take care. Thanks.
Thanks.